I'd like to talk about how we start thinking about solving matrix differential equations and sort of giving ourselves a little bit of a thought process of how do we begin to start working with differential equations in a matrix form. And so just to begin with that, let's start off with a few definitions. Obviously, the lowercase bold is going to be representing vectors, so like an input x, or a weight matrix, which is capital W. So you might imagine something like vector matrix multiplication. Again, a really important concept that shows up pretty much everywhere, and this is a very useful definition, is then talking about multiplying a vector times, taking a vector x times a matrix W. This is going to be this column multiplied by each of the rows on the matrix gives me a column out. Very straightforward from this perspective. Well, what happens when this starts to become a differential equation? So now I've got dx of t equals to ax of t. Well, now I've got a vector and a matrix going into a vector, but now this is a derivative, and I'd like to be able to solve this system. Well, a couple of things are possible. If I'm actually very comfortable with, there's a definition of e to the at, so it feels very much like what I would solve in the scalar case. I can approach that. But another way to think about it is this, is that I have my matrix A. And I might want to say, let me see what happens if I project x onto the sort of normalized eigenvectors of A. And it's a really huge value of working with eigenvectors and eigenvalues. And if one thing that's maybe not always clear when you take linear algebra, but becomes very clear at this stage, is that these kinds of eigenvector, eigenvalue analysis is huge for doing any sort of matrix differential equation solutions. So this is, I almost wish that when one took linear algebra, this was one of the things that you knew going in, because it would be very, very helpful. Like, oh, this is a useful technique. And so one of the things that you find is that if you say make x, you can say make it b, so that eigenvector basis times, which basically would have, say, the rows of eigenvectors of A times some variable x1. So now we're going to have those two things defined. A is going to be defined as a particular structure, E lambda E inverse. And we're going to say, okay, what happens now? Where lambda is a diagonal matrix that has the ordered eigenvalues of the system. And it would turn out that you go, well, is it stable or not? Well, it turns out it's going to depend entirely on how the eigenvalues and their sizes are. And you might go, that's an interesting question. How would I show that? Well, if I know that this is going to be my definition for A in general, I can substitute A in, I can substitute this structure in for A. I can substitute X in for X vector and for the one in the derivative. This gives me this first term on the derivative. The e comes in front of it because it's still a constant. A is still a constant. This is a constant term here, and then this is the remaining term in x1. Well, a nice thing happens along the way that e inverse times e gives me an identity, so it goes away. I get e lambda x1 of t, and the e shows up over here. Well, the e's now, by pre-multiplying the inverse, I can get rid of the e. What does that do? Well, that now gives me this differential equation. dx1 dt is lambda times x1 of t. x1 is a vector. Lambda is, again, a diagonal matrix of this. But this basically turns out to give me the set of scalar equations. x1 at every position k is then just going to be that value at 0 times basically however things shift with the eigenvalues. So the eigenvalues tell me everything. If the eigenvalues are positive, it's going to explode to a very large value. If the eigenvalues are 0 or negative, well, 0 goes nowhere. And if it's negative, it's going to decrease towards 0. And so I can talk about stability. In other words, are all the eigenvalues negative in this formulation? Kind of cool. Not surprising, if this was a scalar, I would say that if that scalar a, again, was negative, this would be stable. If that variable was positive, it would be unstable. It would go off to infinity. So you can get very specific if you were to pick two different values for your A matrix. Again, very, very similar ones. What you find is that Again, unstable is if I have one of the eigenvalues is greater than 0. Stable if all of them are less than 0 in this case. And stability is something that becomes very important in many different places, particularly as you start digging into control theory, whether linear or nonlinear control theory. And in this case, it turns out this matrix has one positive eigenvalue, so you'd call this unstable. And then this one would actually have, two complex eigenvalues, but since the real part is negative, it turns out that they're both stable. And you can start doing this kind of analysis. And this turns out to be very valuable because there's so many different properties and systems where you will look at and go, oh, it could be an arbitrary size input of states. It could be an arbitrary size input. It could be any kind of structure of this, and as you start getting into more complex computing, this is always in the way that you're going to look at the problems. And so it's nice to be able to have a matrix formulation and be able to stay in this space and do sort of proofs at least as far as you can in sort of this matrix space and be able to build up that intuition as you go forward.